All right, so now we haven't yet talked a lot. Well, actually, I don't know exactly how much we know so far about light. Tell me a few things you know about light. Yes?
It acts as both a particle and a wave.
It acts as a particle and a wave. Now, did you learn that in this class or another class?
Chemistry.
Chemistry, all right. Excellent. So what else do we know about light? Because this lab's about light. The purpose of this lab is to measure some properties about light. What else do we know? So wavelength, so if it's a wave, it has a
Speed and wavelength.
wavelength. Okay, so what we're going to do today is we're going to measure the wavelength of light. Now, the light that we're seeing right now comes in all different wavelengths, right? But so the light that we're actually going to measure is going to be from a helium neon laser. So it's what we call monochromatic light. It's a single wavelength. Now, visible spectrum of light ranges from about 400 to about 700 nanometers. So that's very, very small. A nanometer times 10 to the negative 9 meters. So what tool are we going to use to measure the wavelength of light? Well, we're going to use the fact that light behaves like a wave, and we're going to utilize its wave-like properties. So in a sense, what we're going to do today is we're going to replicate Young's famous slit or double-slit experiment where waves can interfere. So let me show you what I mean by this. Oops. See here. Now, there's a couple pictures here which we're not going to really see what's happening here, but I want to show you a couple simulations so we really have a good idea of what we're really doing, and it will make more sense of what we're looking at when we actually do the experiment here. So I'm going to turn on this faucet here, and every time the faucet drips, it creates a disturbance, in a sense, on this fluid, which sends out these blue kind of crests and these black troughs, right? So light, in a very similar way, it has this associated wavelength to it. Now, I could change the wavelength of the source by increasing the frequency. What happens to the wavelength here? Decreases. Increase the frequency, decrease the wavelength. Because the speed of the wave, well, the speed of this wave should depend on the medium through which it propagates. Now, light, as we know, doesn't require a medium through which to propagate. All right, and then I can change other properties such as the intensity of the wave. So that, for us, for light, that would correspond to basically how bright it is. Or basically here, there's a bigger drop, meaning the wave is more intense. All right, larger amplitude. The amplitude is related to really how much energy that wave is carrying, because you can see with a smaller drop, there's less of a disturbance, but it's still a wave, nonetheless. What happens if I now introduce a second source into the picture? Well, with the second source, what we can get is, let me turn these sources on. The sources, since they're waves, they can actually behave like waves. And what are some things that waves do? Properties of waves? Interfere. They actually can pass right through each other. Right? If two particles come towards each other, they bounce off. Or they scatter, we would say in physics. But waves actually pass through each other, and as they're passing through each other, they obey the superposition principle. Meaning, two crests will create another crest that's twice as high. A crest and a trough will cancel out. And you can get these patterns, basically, that emerge, which we call interference patterns. So, when we turn on the first source, here we have our wave. Second source, we have another wave. And we can see those two waves are talking to each other in that there are certain regions where we're getting constructive interference and certain regions where there is destructive interference. Now, let me point out a few features of this graph, because when we're going to be looking at our diffraction pattern, we're not going to see these little blotches moving along here, which would correspond to crests, right? What's the speed of light is 3 times 10 to the 8 meters per second. So that would mean, and the wavelength of light is about 400 to 700 nanometers. So we're talking frequencies which I believe are in the, well, gigahertz range, or we'll have to do the math there, but very, very high frequencies, right? So fast that these are coming at us so quickly that we don't see the individual modulations of each individual crest. But what we would see, if you were standing right here, and these were 2 laser sources producing monochromatic light, what you would see at the center is you would see a bright spot. You would see those 2 waves, or the crests are interfering to produce a bright spot. Now it's true that bright spot and then dim, right? But that's just like the bottom of a trough, and the bottom of a trough is still bright, basically. So basically what you're seeing is this. What we're really seeing is we're seeing the time average. Right? We could talk about the time average gives you a bright spot, or an intensity pattern. Really what we're measuring when we look at a pattern is we're looking at the energy spectrum, how the energy distributes itself over space. So we'd call this a point of constructive or maximum interference. And then we can see that there are, or in a sense, it's kind of like a nodal line. And then you can see that there's this region right here where it's always canceling out. So if you're anywhere along that line, that's going to be a region of destructive interference. And it's going to be a dark spot, or what we call a dark fringe. Now we're talking about light. We can talk about fringe, dark fringe. Here'd be a bright spot, and then there'd be fringes right along these lines here and here. Okay, now I can change the number of, now in our experiment we can't change it because we're just going to be given a source, right? But I can change the number of interference fringes by changing the frequency of the source. So let me turn it all the way up to the maximum. I like to look at the extreme here. And you can see that what has emerged is there's more, essentially, antinodal lines here. You see there's, or destructive interference. And another thing I can do here is I can change the separation between the sources. I can make the sources farther apart. What's happened when I've made the sources farther apart? I've actually got some more interference fringes that you can see here. Okay, so this is the physics of really what we're going to be observing in the lab today. Now what it's going to look like for us is the following. We're going to so the purpose of the lab is to measure the wavelength of light, but let's put a barrier in front of the light. And in fact, since the barrier we're going to start with is 2 slits, let's look at what this would look like. If I send out our light is kind of like our wave generator. It has wave-like properties, so I turn the light. And again, we don't see those peaks and troughs, but when they encounter that barrier, kind of like the drop in our previous experiment, because the wave, the laser acts like is a very collimated beam of light energy. It's all sending in one direction. What the slits, and that would correspond to, this is the laser before the slit. When it hits the slit, the wave begins to spread through those openings in these spherical wavelets, kind of like the drop when it was landing on the surface, and it starts to spread out. And then those 2 sources now can interfere with each other, and we'll have a screen back here, which is where we observe that interference pattern. So our experiment is, this is our screen right here. Your laser is going to be over at the other end of the counter. Right? Be very careful about reflecting that. If you have another group over here, you don't want that light energy reflecting into your eye. You don't want to look into the laser. And then you're going to set up a double slit. And I've given you a number of different slits to choose from. You have to look very carefully. They're labeled here, which one you're going to choose. So there's double slits, there's single slits, and then there's what we call diffraction gratings, which is just basically a lot of slits, right? And they all have slightly different properties, but those properties, when you shine the light through those small openings, it creates a pattern. By measuring the properties of the pattern, you can determine the wavelength of the light, right? And in fact, we'll actually use this to measure the structure of the opening. We'll use the data that we get to also determine, to measure how large one of the openings are. And by the way, diffraction patterns are very useful, right? Does anyone know what we use diffraction patterns for? Kind of in practice? Well, they're spectroscopy, right? They're a useful diagnostic tool for identifying materials. The wavelengths kind of act like a fingerprint, right? And in fact, X-ray diffraction, now we're not going to use X-rays here, we're using visible light, but X-ray diffraction was what was used to determine the structure of DNA, just by shining X-rays through DNA, and that was how that double helical structure of DNA was discovered. All right, now, so let's look at so this is the idea. Now let's look at a little bit of the mathematics behind how this actually works. Now this is in the lab handout, which I'll pull up right now. So I'm going to pull up this figure number 2 on the screen. Is basically illustrating what's happening here. Now these two lines is basically this line right here and this line right here come from each slit, are basically tracking the distance a crest would have to move before it arrives at your viewing screen. Now the key idea here is you can see that the maxima, or the constructive interference fringe, only occurs at a specific spot. That is the spot where should there be a bright spot? Constructive interference, right, exactly. And how do we know when there's going to be constructive interference or not, based on the property of the wave?
When the two peaks line up.
When the two peaks line up, exactly. So what that means is this one is a little bit farther away from that point. So if this wave has to travel exactly a wavelength more than this one right here, then they're going to line up, right? And you're going to get two crests arriving at that point in space at the exact same time. You're going to get constructive interference. Now, not only wavelengths, but double integer multiples of wavelengths. Any integer multiple of wavelengths will give you a bright fringe. Now, obviously, as you go farther and farther up, and you're going to measure all those, they're going to get dimmer and dimmer because the wave has spread out more, but they're still going to add up as long as you're an integer multiple number of wavelengths. The path length difference, we'd say, is an integer number of wavelengths difference. Now, these points, for instance, destructive interference would just be half integer multiple of the wavelength. Okay? Now, how do we actually determine what that is? Well, that's just basically geometry, is how we actually determine where that is. It comes from microscopically. Now, by the way, this picture is an approximation. It's what we call Fraunhofer diffraction or far field diffraction, in that you can basically draw this little microscopic triangle right here and work out that the wavelength equals d sine theta, where d is the separation between the slits. But that is really an approximation for when the screen is really, really far away. And far away compared to what? Well, compared to the wavelength. The wavelength is really, really small compared to how far the screen is away. So it's a very good approximation, right? And then geometrically speaking, so this theta creates a big triangle right here, and that's a macroscopic geometric orientation of where that screen is actually located. So basically, we can determine basically algebraically through some very simple algebra, right, where that interference fringe actually occurs. Okay, just by using this idea right here. So that is double-slit interference. Right, just to show you another picture of what this looks like is, here's the wave coming from the two sources. And if two crests arrive at that point at the same time, that's going to be a bright spot. But if I change, let's see, that you'll see here that that doesn't occur everywhere. So for example, if I'm up here, in fact, you can see a crest and a trough arrive at the top at the same time, right? So that would not be, that would be destructive interference. It would not be constructive. And then, I can find other points of destructive interference. It really depends on where you are, right? Because of this path length difference. That path length difference has to be exactly equal to a wavelength in order for those peaks to line up and for you to get constructive interference. Okay, that's one way of visualizing it. And I want to give you another way to visualize it too, where if I animate the following picture here, you can think of these points as what is emerging from the slits themselves. Okay, and those are all these crests, and you can see where the crests line up. We're going to get bright spots or fringes, we call them, and anywhere in between. So all these dotted lines correspond to constructive interference, and then when you're in between them, you have destructive interference. All right, so that is double-slit interference. Now let me talk for a moment about what would happen if that's going to be what we start out with, but then we're also going to look at what's called, well, let me see if I can pull this up here. Well, let me pull up the picture here, is what happens basically if I start to add, so 2 slits, 3 slits, these interference fringes, there starts to become more regions of destructive interference. So what happens? 7 slits, and we're going to have thousands of slits. So these spots become narrower and narrower because there becomes fewer and fewer spots where the interference is constructive. There's a lot more regions where it's destructive interference, right? Because when 2 slits talk to each other, there's only specific places where they interfere. When you have 3 slits, there's going to be destructive interference between slits 1 and 3, for instance. There's other regions where it cancels out. So what it does is it narrows these fringes, and that's why diffraction gratings are used in spectroscopy to determine the atomic or the molecular composition, or they act like a fingerprint in astrophysics, right? To determine the composition of materials is because you get these spots occurring at very specific spots that basically tells you what electronic transitions are taking place and what element you have. All right, so that is the diffraction grating, and what those look like for you is, you're just going to choose between a few of them. 300 lines per millimeter. And why does it say lines per millimeter? Well, it turns out that, well, it's just a bunch of basically scratches on the surface here, and or a bunch of parallel openings. So you're going to look at the diffraction pattern there, and from that you're going to be able to make a few predictions about the spacing of the diffraction grating. All right, finally then I want to talk about the single slit, because that's what you're going to do at the very end. The last part of the experiment is the single slit. Now, you might ask the question, well, why does a single slit have any diffraction to begin with? Well, if I send a wave, actually let me go back here for a moment, because I like this picture. I'm going to go to, that's 2 slits, 1 slit. Right? If I have just 1 slit, you can see that what happens is this wave, actually, when it encounters that small opening, it starts to spread out. Okay? And this creates a diffraction pattern. So I could, again, change the size of the slit. look at, there's very interesting things happening right at the edges of the slit. But if I make the slit really, really wide versus, you can start to see that there's some darker regions out here, right, where not much is coming. But if I make the slit really, really narrow, what happens in this case is the wave spreads out a lot more behind that point. It almost spreads out to fill all space behind that point. So what emerges is this diffraction pattern. Now, let me just explain to you just give you an idea of why this actually happens. So this is called, this can be thought of something that we call Huygen's principle, which basically says every part of an advancing wavefront is a new center of disturbance. So we can consider every point of a wavefront as a secondary source of spherical wavelets. So what does that mean? That means let's consider this to be our opening right here. Now, an opening, if we break it up into a bunch of little points, and then we add all those points together, using the superposition principle, there's going to be a lot of interference which takes place. And that's why we get a diffraction pattern on a single slit. So I'll show you an animation here which illustrates this, which I think is helpful. So as the waves emerge, every little point that's coming from that hole acts like another spherical wave. And all those infinite number of spherical waves are interfering with each other. And what you can see, what you get here is you get this spreading wave with these wavefronts with crests and then troughs in between. Now if I put a screen here, right, you would see that there's going to be spots where it's intense and the spots where it's less intense. Or spots where it's spread out more, spots where it's spread out less. All right, now finally, this is not something we'll see directly in this experiment, but as was pointed out right at the beginning was this wave particle duality of light in that, okay, so here we're only really looking, here we really only have the tools to examine the wave-like properties of light, but light also behaves like a particle, which can also be shown through this experiment where I can do the same experiment with light where I decrease the intensity such that just a single photon is passing through the slits at once. And what happens, very interestingly enough, is you still get this diffraction pattern. Even though light, it seems like it's a paintball. You know, just one splotch of paint emerging at a time as it's illuminating the photodetector. You still get this interference pattern. All right, so what I'm going to do here is I'm going to dim the lights, and I'll keep them on for a few minutes here just as you get your orientation with the data that you're going to take. Now, the very last part of the experiment is someone's going to have to volunteer a piece of their hair, and you're going to tape it over the opening of this CD, and you're going to shine laser on that barrier. So that barrier, that hair is going to be the barrier, and it's going to basically diffract around the barrier. Now it turns out the diffraction pattern through a small barrier kind of turns out to be the same as the diffraction pattern through an opening. So you're going to look at the diffraction pattern on the screen, and what you're going to find, that's going to allow you to measure the diameter of a piece of hair. All right, so let's start with that.